The fifth section is on complex conjugates. The complex conjugate, or simply we also say just conjugate, of a complex number z, which is say x plus iy, is this complex number x minus iy, and we denote it by this notation z bar. So that means the complex conjugate of z is obtained by changing the sign of the imaginary part. Geometrically, the number z bar is represented by this point x comma minus y in the complex plane, which is the reflection of the point z, or more accurately this point which represents the complex number z in the real axis. For example, say your complex number is here in the complex plane, then the complex conjugate of that number, when you consider it as a point in the complex plane, will be the reflection of this point in the real axis. This is a simple property of conjugates, that if you take the conjugate of a complex number, then you get the complex number back, which you can see pretty easily. If our original complex number is x plus iy, what is this inner conjugate? X minus iy. Once more you take conjugate, then you get back x plus iy. Next, let's consider the absolute value or modulus of z bar, which is absolute value of x minus iy, which by the definition of absolute value is the square root of x square plus minus y square, which is nothing but this. This, however, is just the absolute value of z. So a complex number and its conjugate have the same absolute value. Next, we want to see how complex conjugate behaves with addition, subtraction, multiplication, division, these things of complex numbers. So we take two complex numbers, z1 which is x1 plus iy1 and z2 which is x2 plus iy2. Let's first calculate z1 plus z2 bar. z1 plus z2 is of course this by the definition of complex addition. And then you take complex conjugate, that means you change the sign of the imaginary part. So you put a minus sign here. And then after rearranging things, you see that this is nothing but x1 minus iy1 plus x2 minus iy2. So that is just z1 bar plus z2 bar. So complex conjugate distributes itself over complex addition. This is a very nice property. It simplifies calculation. In a similar manner, complex conjugate also distributes itself over complex subtraction, which you can prove exactly like this one. I am leaving that to you. Next, we see the relationship between complex conjugate and complex multiplication. Say we take the product of z1 and z2, which by the definition of complex multiplication is this complex number x1 x2 minus y1 y2 plus I times x1 y2 plus x2 y1. So that means its complex conjugate will just be this complex number. You just replace this plus by minus. And now next we are going to calculate z1 bar times z2 bar, and let's see if we get the same complex number. So this is the calculation. z1 bar is x1 minus iy1 and z2 bar is x2 minus iy2. So same formula, real part times real part minus imaginary part times imaginary part. Here the imaginary part itself is minus y1 and here it's minus y2. So that's why it looks like this. But the form of the formula should be the same. The multiplication formula I am talking about. Plus I times real part times imaginary part. So you have a minus y2 here, plus for this one real part times imaginary part, x2 times minus y1. So these two minuses give us plus. So you survive with a minus sign. So you have x1 x2 minus y1 y2. And if you take these two minuses outside, then you get the exact same thing. Hence we have this equality, that is complex conjugate also distributes itself over complex multiplication. And a similar formula is available that involves complex division, and of course with the usual caveat that the denominator should be non-zero. I am leaving the verification of this one to you. Next, let's consider a complex number x plus iy z and take the product of that and its conjugate. That means x plus iy times x minus iy. And we apply the usual formula in the definition of product. real part times real part minus imaginary part times, here the imaginary part is minus y, okay, we have to keep that in mind, plus I times real part times minus y plus x times y. So you can see that this part vanishes. Here there is no imaginary part and this becomes x squared plus y squared, which however is nothing but the square of the absolute value of z. So you have got a formula involving absolute value and complex conjugate. In particular, if your complex number z is non-zero, then both sides are non-zero. So that means this is non-zero and z is of course non-zero. So you can divide both sides by z times the square of the absolute value of z. If you do so, you get this. 1 divided by z becomes equal to conjugate divided by square of absolute value. In this way, you find a way of calculating the inverse of z, the multiplicative inverse of z, as this. And this further gives you an idea for doing something else also, which is similar. Suppose you have a quotient of two complex numbers, z1 and z2, where of course z2 is non-zero. Now you want to simplify this quotient in such a way that you end up getting a real number in the denominator. Or in other words, you have to do something so that ultimately you can express the complex number in the standard form, real part plus I times imaginary part. For that you have to get rid of this z2, which is a general non-zero complex number which is in the denominator. So what you do, by what you saw just now, by that formula, you can think of bringing this in the denominator, the square of the absolute value of z2. For that you multiply and divide by the conjugate of z2. Can you do that? There is always the danger of unknowingly dividing by 0. What is given to you is that z2 is non-zero. Does that imply that z2 bar is also non-zero? Yes. I leave it to you to figure out why. Okay. Anyway, let's accept that this is non-zero and we can multiply and divide by it. Now the denominator becomes this quantity, which is a real number. The square of the real part of z2 plus the square of the imaginary part of z2. So that's the real number, and actually that's a positive real number in fact. And in the numerator you have whatever you have. So in this way you can do simplifications where the expression looks like this. Let's see this method of simplification in a concrete example where the complex number z1, in place of z1 say we have minus 1 plus 3i, and in place of z2 we have 2 minus i. So we multiply and divide by the complex conjugate of this, which is 2 plus i, and then we do the multiplication in the numerator, which you can do in two ways. Either you can apply the formula means the definition of complex multiplication, or you can do your usual algebra way. As we saw before, this is also legitimate. So I adopted that. Okay, I just simply multiplied out the terms. If I multiply this by minus 1, I get minus 2 minus I plus 3i times 2 is 6i plus 3i squared. And what should be the denominator? By that formula that we derived there, the denominator is the square of the absolute value of 2 minus I. Or if you want, here also you can do multiplication. That is also allowed. But anyway, it will be just this, which is what? 2 square, real part square plus imaginary part square. Here the imaginary part is minus 1, not minus I, okay. The imaginary part itself is a real number. But anyway, so what do we get? The numerator then becomes minus 2 minus I plus 6i is 5i, and I squared is minus 1, so minus 3. That means minus 5 plus 5i, and very nicely the denominator is also 5, 4 square plus 1. So after cancelling that, this is your complex number in the standard form, minus 1 plus I. So we multiplied a complex number with its complex conjugate and got something, namely the square of the magnitude. Magnitude means absolute value. I should not say magnitude. But what if we add, say the complex number is x plus iy, we add with it its complex conjugate. Then cancelling this iy and minus iy, you are left with 2x or 2 times the real part of z. So you have got this one, a new formula which expresses the real part of the complex number in terms of the complex number and its complex conjugate. And similarly, if instead of sum one takes the difference z minus z bar, then one gets 2i times y, or 2i times the imaginary part of z, because y is the imaginary part. Or in other words, imaginary part of z equals z minus conjugate of z divided by 2i. So you have expressed the imaginary part in terms of z and its conjugate. Do not forget this I, okay? Sometimes we forget this I, but that's wrong. We can milk the relation between conjugate and absolute value even further to prove a property of absolute values. Let's consider the square of the absolute value of z1, z2. By that relation, this is the product, here the complex number is the product. The complex number times its conjugate. But as we have already seen, and in fact we proved, that this is equal to z1 bar times z2 bar. So we now have this. Then after rearranging things, why can you rearrange? You can rearrange because complex multiplication is commutative and associative. That is why. But anyway, so you bring z1 bar with z1 and move this z2 over to z2 bar. This is z1, the magnitude of, why do I keep saying magnitude? The absolute value of z1 square times the absolute value of z2 square, which is the square of the product of their absolute values. And then we have this observation. This as well as this are both non-negative real numbers, and that is why we can take non-negative square root on both sides. Doing that, we get this. So you have this identity involving complex multiplication and absolute value. This does not involve conjugate, but we used conjugate to prove this. Similarly, the absolute value of quotient, the quotient of two complex numbers, equals the quotient of their absolute values in the same order, provided of course that the denominator is non-zero. You can prove this one exactly like this one. And finally, the section ends with this example. Let z be a complex number inside the circle with radius 2, which is centered at the origin. Okay, so this is in the complex plane. Say the complex number z is somewhere inside this circle, which is a circle whose center is at the origin and whose radius is 2. Then the distance of the point representing z from the center will be less than 2, which however is nothing but the absolute value of z. So that should be less than 2. Now the question is this: can we use this to say something about this? The absolute value of this complex number, z cube plus 3z square minus 2z plus 1. First we apply the extended version of the triangle inequality, which involves absolute value. Absolute value of sum is less than or equal to sum of absolute values of the individual terms whose sum you have inside the absolute value. So that way you are getting this. And then in the next line, what did we do? We used what we proved here today. Product of absolute value equals absolute value of products. Or I should have said it this way: absolute value of product equals product of absolute values. So this 3 comes outside. Just like that, here actually you can think of 2 steps. In the first step you write absolute value of 3 times absolute value of z square. Absolute value of 3 is nothing but 3, and absolute value of z square is square of the absolute value of z. Just like that, here you have mod minus 2 times mod z, mod minus 2 is 2, and here you have mod z, and mod 1 is of course 1. And then you use this inequality. And from that you get that this expression is less than this, which turns out to be 25. So this is another complex number just like that, which satisfies this inequality means what? That it will be somewhere in the complex plane, wherever it will be inside such a circle whose center is also at the origin and whose radius is 25. It's a much larger circle, but inside that circle somewhere this complex number will be present.